Welcome to radar system course. So we see here a noise figure. So noise figure is depending upon that effective noise temperature, and that effective noise temperature consists of a noise temperature of each and every component present in a cascade. So this one is the T1, a noise temperature of network 1 component, network 2, this one, network 3 likewise. So for every component there is some temperature. So we need to monitor a noise figure of a radar receiver, because the temperature of each and every network can be varied while receiving the echo from the target, because once the device is on, so every time the temperature will not be fixed. So that's why we need to monitor the noise figure of a radar receiver, because in operation there may be a variation in the temperature. So that's why a noise figure will be changes there. Therefore we need to monitor the noise figure. If a noise figure is not monitored by the user, so in that case a sensitivity of a receiver will be degraded there. So to achieve this, or to increase the sensitivity of the receiver, so we need to monitor the noise figure by automatically or by manually. So for that purpose, for a receiver, whatever the network components present, and then we need to find out for each and every component that noise power output of the receiver with a matching condition, and a noise power output of this component we need to find out. So for example, if we consider that there is a receiver tube, and for this we have a receiver network, and we need to measure the noise figure of the component. So we can find out for a given particular network or any component. So there will be the noise power output, that will be the N1, will be the noise power output, and that noise power output we are getting when the device is connected to the receiver at a matched condition. And then that particular given match condition, we are getting the N1. And then we need to find out that a noise power output N2, when a noise power generator is matched for a given particular temperature value of a T2, and that is connected to the receiver input. So this one is for the T1, it is connected to the receiver input, and this one is for the T2, it is connected to the receiver input. So then we can find out through this what will be the noise figure. Noise figure is nothing but what? A ratio, whatever we have absolute temperature we are supposed to consider, T2 by T0. So this one is about a match condition with absolute temperature. So instead of that we can write T0 here, so at absolute temperature. And then after some times we need to measure the temperature of the device at a given noise power, and at that time temperature will be a T2. So that's why T2 by T0 minus 1 divided by N2 minus N1, N2 by N1 minus 1. So this will give you the a noise figure of the system. So this one is what? Initial condition, at absolute temperature, and while using the receiver, after some time the component temperature will be increased. So that's why at that particular point what will be the signal noise power, and then from that we can find out the a noise. So this will be useful for the verifying the sensitivity of the receiver or increasing the sensitivity of the receiver during the radar operation. Then another component of a radar receiver we need to understand, that will be the a mixer. So we can consider here a super heterodyne type receiver. Okay, so our receiver, or we can say that super heterodyne type receiver, and they at a input stage of the that super heterodyne type receiver, if you consider, so there will be the mixer at the input stage of a receiver. There will be the mixer. Okay, so after immediately after the antenna, there will be the mixer. So what particular component present at a receiver? Okay, so we can see that here the receiver, we say that this one is about a mixer. For the mixer, we are supposed to provide a signal from the local oscillator. This one is about our antenna. Now at this particular place, if you consider a signal, echo signal from the target when reached to the antenna, then first component will be a mixer there. Okay, after the antenna, there will be the first component will be the mixer. So for the given particular mixer, input is present here. So what will be the output of the mixer? This one is nothing but the input. This one will be the output. Generally, a mixer produces a two component, that is a sum and difference component. So how to measure the efficiency of a mixer? Because it convert that a input signal, and that will be used to the IF. Okay, because output is given to the IF here, intermediate frequency. So it will convert a signal, okay, into the IF here. So we can find out the efficiency of the mixer based on the conversion of the RF signal power into the IF here. So in that case, what will be the available power at this mixer, and then whether it will convert, what will be the power available at the IF power, that will produce you the what will be the loss at a mixer there. So conversion loss, okay, LC is nothing but what? A conversion loss. Conversion loss is equal to what? What will be the available power? That is available RF power divided by a available IF power. Okay, that is about it. Available IF power. So that will give us the what will be the conversion loss there. Now the conversion loss is depending upon the noise temperature of each and every component. So in a mixer, generally we can consider that it is to be operating at a highest frequency. So that loss is depending upon that what type of a local oscillators we are using, because that local oscillator is to be operating for a broad band of a frequency. So, so mixer is nothing but what to be called as a broadband crystal mixer. So when we provide a stable signal to the mixer, okay, from the local oscillator, so it will convert the signal with a sum and difference component, or in another way we say that we are getting the image frequencies from this. So from this we can find out, so what will be the a conversion loss. That image frequency is nothing but the smallest variation in the local oscillator frequency. So that what will be the smallest variation in the local oscillator frequency? That will give you the, or that will depending upon the a local oscillator, crystal oscillator. So that a conversion loss of the mixer will be increased or a decrease. So mixer is used for what particular operating frequency, and what will be the available power, what will be the power generated by the mixer. So what type of a configurations or what type of a components we are using in this mixer, so that will provide a sufficient power for the IF. Otherwise what will happen? So IF is not detecting the signal. So we need to consider the device so that it will generate a available power for the given particular IF. So device used in the mixer, that will be of a low noise figure. Okay, so we can consider a mixer, as well as we can consider here the local oscillator. So we can consider those devices, they are a low noise figure there. Generally a diode. Okay, so you can say that a Schottky barrier diode, or we can say that a point contact diode. These are used in a radar receiver, and they have the low noise figure. Now we can consider a mixer. At input, what happens? Signal come from the antenna that will reach to the mixer. But sometimes what happens, because the single antenna we are using most of the time, same antenna is useful for the transmitter and receiver. So in that case, sometimes if high power pulse generated by the transmitter, if that pulse will reach to the mixer, because here is the diode, so that will be damaged because burnout takes place at a receiver there. So in that case, we need to take care of that burnout, as well as the what will be the operating frequency. So what will be the noise temperature? Okay, so we can calculate for the given mixer here. So that will be depending upon that what will be the actual available IF noise power. This one is about a noise temperature ratio of a crystal mixer. It is equal to what? What will be the actual available IF noise power divided by available noise power from an equivalent resistor. So in that case, we can write TR is equal to what? FC. FC is nothing but what? A crystal noise figure. Then a K, your temperature, T0, K Boltzmann constant. Then this one is the temperature here. Then a noise power bandwidth here. Then we have a GC. GC is nothing but the gain here. And then a K T0, that is a BN. So we can write here FC into GC or is equal to FC by LC, because we can say that LC is about a conversion loss is depending upon the 1 by a GC here. So this will provide you the what will be the noise temperature ratio of a crystal mixer. Okay, that will depending upon the a conversion loss, and this noise temperature that will be depending upon that what particular diode we are using at a local oscillator, and this noise temperature will varies inversely with the frequency from about the 100 kilohertz. So in terms of a broadband one, so this one is nothing but a small fraction of the frequency is there, and that mixer will used. Okay, and this particular small fraction of a frequency that crystal mixer is used, and that small fraction of frequency is called as a flicker noise, or we can say that it is called as a 1 by f noise. Okay, this one is called as a flicker noise, or we can say that a 1 by f noise. Okay, and that flicker noise is depending upon the what will be the noise temperature for a given particular IF range. Okay, so we can the for a given particular crystal mixer, and that will be provide you the what will be the available power at the IF here. So in general, we can say that a noise figure of a mixer, that FC is equal to what? Depending upon that temperature as well as the conversion loss here. So means generally we say that a noise figure overall for the circuit. So what will be the noise figure of a receiver with a mixer front end is equal to F0 F1 plus F2 minus 1 by 0. And in this case, the first network is nothing but what? We have the a mixer there, and that mixer, it has a noise figure of what? ATR and LC, and it has a gain of what? 1 by LC. Okay, earlier we say that the gain is equal to 1 by LC, and the TR is nothing but the a temperature for what? A noise temperature ratio of a crystal mixer. Then gain is equal to 1 by LC. So first network is nothing but a mixer, and second network is nothing but what? A IF amplifier. And that IF amplifier, it has a noise figure. IF amplifier, so it has a noise figure of what? AF IF. Means we have the receiver component. We say that first component is about a mixer, means belongs F1 belongs to the mixer, and this one is belongs to the IF here. So total noise figure F0 is equal to what? F1 from the mixer, and this one is from the IF here. So if you solve it, because this one belongs to the mixer and that mixer has some particular conversion loss. So LC plus, we can LC and we can say the TR plus, what will be the FIF here? Minus 1. Okay, this one is nothing but a noise figure of a receiver with a mixer front end. Okay, so it consists of what? A conversion loss, and it consists of this, what will be the noise figure of the IF. This TR is nothing but what? A crystal noise ratio. Okay, noise temperature ratio of a crystal mixer. Then a noise, we say that came from the mixer, crystals and all. So instead of that, we can use to remove the noise, we can use a balanced mixer there. Okay, so we say that a noise is present, that noise from the local oscillator that will be available at a IF here. So that's why we need to remove that whatever the noise from the local oscillator, so that a sensitivity of a receiver will be increased. So noise generated present at a local oscillator that again pass through the IF. So that's why IF again it will reach noise. So that's why receiver sensitivity, probably we can say that in terms of it, how that IF is used. Okay, how your IF is worked there. So we consider that a removal of a noise or suppressing the noise from the local oscillator that will pass through the mixer to the IF. Okay, because we can say that this one is about antenna. Here we have a mixer. Then we can say that a IF. This one is about a local oscillator. Because a crystal local oscillator, there is a noise temperature ratio of a crystal local oscillator. Okay, so we can say that through this there will be the flicker noise, and then that particular noise will propagating toward the IF. So conversion loss is depending upon that what will be the noise from this local oscillator, and at this particular IF the noise available from this local oscillator, and that will reduces the efficiency, or that will reduces the sensitivity of a receiver there. So to improve this or to suppress that particular a noise, we need to use a filter at this particular a narrowband filter, so that whatever the noise generated from this local oscillator that will be removed through the air narrowband pass filter there. So where we are using the narrowband pass filter, so either because it generates a sum and difference component. So here we have what? A F1 plus F2 or F1 minus F2, and IF is available. So that consists of what? A component of local oscillator and mixer. So if we are using a filter here at a local oscillator, in between the local oscillator and mixer, that is called as a, what we can say that we use a narrow band filter. Okay, so we can use a narrow band filter. Okay, this one we can say that a narrow band filter if we are using. in between the local oscillator and mixer, that will use to eliminate the local oscillator noise, and that noise will not be reached toward the IF. Okay, so IF some particular frequency signal will reach. So we can consider a filter to remove the noise there. So that narrowband filter consists of what? A operating frequency that will be related to the local oscillator there, and that bandwidth will be very narrow, so that whatever the noise generated by the local oscillator at the given particular signal frequency as well as the image frequency, that will not appear at the mixer there. So we can say that a receiver we have, that receiver we can tune using the local oscillator. While tuning the receiver using the local oscillator frequency, we need to tune a narrowband filter as well, so that a local oscillator noise will be removed. So now we need to introduce a narrowband filter here for removing the local oscillator noise. So instead of that, we can use a mixer, balance mixer, and that balance mixer, so that the noise will be removed here. So either we can use a narrowband filter or we can use a balance mixer, and then we can consider that a that device, okay, with a balance mixer, and that will be used to remove the a noise there. So it will eliminate the local oscillator noise. So what will be the component used in a balance mixer? Generally, a balance mixer is nothing but a hybrid junction, and that hybrid junction is nothing but what? Magic T. Okay, or we can say that a four-port junction. And for this particular four-port junction, we provide a local oscillator signal as well as the RF signal to the two port of this particular magic T, and then we can get the signal across this particular mixer. Generally, we say that a mixer produces a two components. Okay, so similarly, a balance mixer is supposed to consider the a magic T. So generally, we know that a magic T is nothing but a we have this main waveguide or auxiliary waveguide, and for this auxiliary waveguide, so this one is about a magnetic field arm. You can say that the E arm and the H arm here. Okay, so we can say that this one is about a magic T. So for the magic T, these are nothing but what we can say that a E arm. This one is about a H arm, and this one is nothing but the auxiliary waveguide. Okay, we can say that. Okay, so this one we can consider that the about a waveguide now. So we provide the two input, one from the local oscillator and another from this RF signal. So that, so in general, if you consider that antenna, then we have a mixer, then we can consider that is about a local oscillator. So one signal to the mixer is what? A local oscillator, another signal from the a RF here. This RF, this one from the local oscillator. Now this magic T, you know that this one is about a main arm. So if we provide the input at this particular arm, power is equally divided at 1 and 2, but it will be out of phase. If you provide the input at this particular arm, power will be equally divided in 1 and 2, but it's about same phase, but no available power at this particular arm. Means if we provide the input here, no power available here. If you provide the input here, no power will be available. So the role of a mixer we consider here. So in which a local oscillator power or a local oscillator is to be applied to this H arm here and the RF signal, because that will not available at this, and the RF signal is applied to this one. Okay, so local oscillator signal to the H arm, RF signal to this E arm, then power will be mixed here. Okay, so this one is nothing but what? It will be mixed here at this particular collinear arm, and that collinear arm length will be the same. Okay, these two particular arm, again the same here. When we apply the power, so we supposed to consider a mixer uh, in this particular magic T balance mixer. So we can consider the a diode mixer in the these two arms. We can see that we have a diode mixer here. Okay, likewise, we can say that in upward direction or a downward one. So in another case, if I draw this one, so we can say that a local oscillator signal. Okay, so this one is upward one. Okay, so likewise, power will be here. So in this case, we can say that diode will be a likewise. Okay, so we can say that. So this way we can consider the a magic. We can apply the local oscillator signal here as well as the RF signal here, and it will produce the signal that will provide that will be available at the IF. So this one is about a local oscillator signal LO as well as the RF signal at this particular place. So signal in the forward and backward likewise. So one diode at one arm, these are the two arm collinear arm. At one arm, one diode, another arm, another diode. Means the diode will be used as a mixer here. So in the case here, so one of the diode will be act as a summation of the RF signal as well plus local oscillator signal, and the another diode will be act as a difference of this RF and yellow signal. Means we are getting a two output. One output is summation output, another output is a difference output. So here the mixer output will be a summation as well as a difference one, and that will be available at a IF. So we can consider that after that the signal will be available at the IF. So here we have the sum and a difference component. These are the two diode mixers that will provide you the output at the IF, because this one is connected to the IF. One is for the local oscillator, one is for the RF, and these 1 and 2, these are the collinear arm we consider that is to be connected to the IF here. So whatever the noise is generated at this particular local oscillator here, that noise will be cancelled because of this mixer, because when it will reach to this particular place, so in that case a local oscillator noise at this two particular diode will be in phase, so that's why it will be cancelled automatically there. So local oscillator noise will be suppressed by using this a balance mixer, and that particular noise is called as the AM noise of the local oscillator, and that will be cancelled by this a balance mixer. But a FM noise that will be inserted by the local oscillator, that will not be cancelled by this balance mixer. So this one is useful only to cancel the AM noise generated by this a local oscillator. So this one we can consider one as a magic tee for the balance mixer there. Here we have the two ends. One end it is generating the sum and difference component. One sum component, another is a difference component. So instead of that, we can use a single-ended mixer. So it will generate. So single-ended mixer means we are interested only in a one diode mixer, not two diode mixer. So where we are interested in sum or a difference component there. So these are about the we can use a two component, one diode or a two diode mixers in a balanced mixer. If we are using a single diode mixer, okay, single component, single ended mixer, in that case that local oscillator noise is to be cancelled by inserting the appropriate device at this that particular match condition, so that that noise will be removed. So double balance mixer basically it will use to remove the local oscillator noise state. Okay, that is about suppressing the a noise generated by the local oscillator. Or we can use a termination so that a noise can be removed. Okay, so there are the various approach, so that through that we can improve the sensitivity of the receiver, or we can say that we can increase the sensitivity of the receiver there. And we can say that to increase the sensitivity of receiver, so here we can consider the mixer, what type of mixers we are using. So either we can remove the noise that will be generated from the local oscillator, or we can say that at a mixer we need to consider a proper match termination or match condition is to be used in a mixer, so that a conversion loss at this particular place will be reduced. So that's why we can say that a sensitivity will be improved. So means at this particular stage here, the conversion loss and a noise figure at this particular place is to be a less than the 1 or a 2 dB there, so that a mixer sensitivity will be improved here. So how to improve this mixer sensitivity? So for receiver sensitivity, we need to consider that a reactive termination in a match load, so that whatever the image frequency is present, that will not affect the a conversion loss as well as the a noise figure there. Okay, so we can say that whatever the signal, because our aim is here, it is to be generated or available power at this particular IF, whether that available power, that will be depending upon the, we can say that a conversion loss as well as the a noise figure. Okay, so we can use a image frequency termination, proper image frequency termination, so that image frequency generated, okay, that will be through the local oscillator, we say, and that will be available at the IFM. So proper matching or proper termination is used. We can say that a reactive termination is to be used instead of a narrow band filter, so that we will increase the sensitivity of the receiver. So how we can provide the this particular reactive image termination there? So for that purpose, we need to understand that how to provide the a termination there. So one, we can consider that the RF here, we have a diode mixer. So this, for this one is, we can say that, okay, so this one is a diode mixer. Then this one is about a 90-degree hybrid junction, and for this junction it is to be matched one. This one is called a termination, and we provide a local oscillator input. Then we have a it's another diode mixer. This one is useful for the image recovery, and that image recovery, that will be available at the IF, because we can say that whatever the signal reactive termination we are using, and that will convert the image frequency, that will be reflected back through the mixer, and it will be available at the IFM. This one is about a 90-degree hybrid junction. There is no any issue of a phase and all, so that it will be available at the IFM. Okay, this is just like a similar explanation we have seen earlier for this magic T junction. So this one we consider that a hybrid junction, and that will produces a 90-degree of a phase difference between the local oscillator and this particular two input to the mixer. And then that will be available at again a 90-degree phase apart, so that it will produces output at the IFA. And this particular mixer is capable for the wide bandwidth. Instead of using a narrow band filter before after local oscillator or in between the local oscillator and a mixer, so we can use this type of mixer, so that that mixer can be useful for the wide bandwidth as well as in increasing the receiver sensitivity. And this image recovery mixer is used at a receiver front end, because we require a high dynamic range and the low intermodulation products, less susceptibility to burnout, and as well as in terms of a cost, that will be in low here. So these are about a radar receiver and a balance mixer as well as the image recovery mixer. So with this we stop here. So thank you all. So